Okay, thank you. So I'm going to present some work I've done with Amy Jalsenius, who got her bachelor's degree this year, actually. And it's kind of funny, but Sam and I work in the same town, and we were completely unaware of us working on the same problems, actually, until last year. So, and we come from very different directions. I know there's a clear reason for Sami's work on this, which is completely different from mine. Yet it's the same problem, but we at least come up with different solutions. So you will hopefully enjoy this anyway. Now, both Tandy and Sami has kind of motivated this work nicely, I think. So maybe I should not spend so much time on this, but for various reasons, we want to work with distance-based methods sometimes when inferring phylogenies. Everyone knows that these methods suck. Rather, if you want to do phylogeny, you use probabilistic methods, but these things are useful anyway. So that's my reason for working on this. And of course, the method we keep coming back to is neighbor joining. And it's because it's been the most successful. It's in very many different ways. It's also simple, and I think that's one of the reasons for its popularity. I'm trying to, so it's based on this selection method, right, that we're probably all familiar with. And in neighbor joining, you simply take pairs, minimizing this selection function, and then you're happy with it and iterate. But it's slow because it's iteratively this way, and so it's got cubic time complexity. But on the plus side, it has some quality guarantees that are nice, and this is the artisan convergence radius that guarantees that if you have branch length B, being the smallest branch in the true tree, and the errors are less than half of B, then you are guaranteed that the correct tree will be inferred, which is super nice, of course. And I want to mention some of the things that Sami mentioned here too. Fast neighbor joining by his supervisor Jens Lagergren is interesting. It takes ideas from Atterson's proof on the convergence radius to get quadratic time complexity and something neighbor joining inspired, but it doesn't perform so well when you wear off from high quality distances. And then you have a rapid NJ, which I think one should mention because it's super fast. And often in practice, you get basically quadratic time, running time. And more recently, rapid NJ has been well engineered, one might say, by a group that added parallelization and various other optimizations to be able to compute initial trees for COVID phylogenies. However, again, the bad news is that these methods all need distance matrix, and that really kills the inference speed. That's a big pain. So if you want to do fast inference, you have to avoid computing the whole distance matrix somehow. I ended up thinking about this coming from some completely different problem, but seeing it, I suddenly realized that there is a divide and conquer solution to this problem, which I now want to show you or try to go through. So we have a base case. If there is a small number of sequences in our input, we'll just run neighbor joining or actually whatever else we would like to do. But if it's larger than that, I'm going to pick 3 sequences randomly from the input and create a tree on that and pick a center. And this center is important, actually, because it will define our some subsets. And now when we have this initialized, we'll go through all the other sequences to figure out where those sequences belong. What is their best friends in this trivial tree of 3 sequences? Is it sequence 1, 2, or 3? And we're assigning the sequences to these 3 subsets based on where the neighbor joining selection method thinks they fit best. And then we go and compute these trees recursively. And the nice thing is that with this construct, we have the center sequence being part of the 3 subsets, and that's the only thing that joins them. But if we now have, say, perfect trees built on these 3 subsets, we can just go ahead and join them on this shared taxa. So the C vertex here is not the sequence, mind you, it's simply a virtual sequence, ancestral sequences. But it's easy to join them on C and just return this tree. And it's what makes this good is that we have only O of n distances inferred here. We do not need the whole distance matrix to assign sequences to these subsets. And I want to highlight that this method is super easy to implement. I did it myself in Python. And occasionally, the experience is that this behaves like n log n time if the tree is relatively balanced, which it is most of the time. If you're smarter than me, and there is plenty of you in this room, you can probably prove that the expected running time is n log n, but I haven't gotten to that. But at worst, at least, this is quadratic scaling. But empirically, we're avoiding huge amount of distances from the distance matrix. So in this graph here, and you see when it's approaching from 4,000 leaves there, we're getting almost no distance estimations done, which is helpful for speed. And also, due to the way this is set up, we can get Atterson's convergence radius, meaning that with good distances, we're guaranteed that you get the true tree. And this is something you can see in this very basic quality assessment that I made. I've done much more than this, but I don't have time to show you all of them, but some more stuff will be shown soon. But here, I just construct a tree, and basically all the branch lengths in this tree as a distance 0.1, and then I impose errors on this very randomly. And then I see if I can infer this correct tree. And as you see, no, I can't show you that, but with a small error, well, then it behaves as it should, and the Atterson performance guarantee is actually working, which is fantastic. But then, of course, when we start adding errors or increasing errors, it goes haywire, whereas, as you may see in purple, neighbor joining is doing just fine. Very annoying. Why is this? And if you're familiar with Robinson fold, you will know that the relative error or relative Robinson fold's distance of 0.8 is horrendous. I mean, you don't want that. But so, well, if we can get good distances, just like with Semi's work, yeah, then we'll do fine. But for the kind of use case I have in mind, we don't have good distances, actually. So the reason for it being so bad, but fast but bad, is that we're only making use of a small number of sequences when assigning sequences to the subproblems. Compare that to neighbor joining. Both of these methods are greedy, making lots of greedy choices, but neighbor joining is making use of all its data when making any kind of greedy choices. So I was getting to think, maybe it's possible to find a middle way there. And this is where I talked to Amy and asked her to work on this. And she came back and delivered this super nicely. So here is the basic construct now that we scale this up a little bit. So instead of picking 3 sequences, we now take a larger number of starting sequences to build a tree of, and I call that the core set of sequences. So k. Think of it as 100 or something like that. And then on this core set, we compute the core tree. And you can think of it like a guide tree, but I don't think that's a good terminology here. But in this guide tree, we also compute the center or centroid. And this center is going to define the subproblems or initialize the subproblems. So the core set of sequences is split up in these 3 subsets. And then, and I follow with the animation here, all the other sequences are assigned to these 3 subsets based on which mate that the neighbor joining selection function thinks is good for them. So again, we've ended up with 3 subsets of sequences. And that you see on the recursive step, the second to last line in this algorithm, we're adding the center sequence here and do some tricks with distances for this to work. But we can apply this recursively. And then we get back trees again, sharing this centroid node that we connect them on and return it. So how well does this work then? Well, on the left, you have the same graph as I showed you moments ago. And on the right, with a completely different Y scale, you have this DNC3K algorithm or core tree algorithm. And you can see that as this parameter K goes up, here we use the base K size being the same as this parameter K, which we're using for choosing the starting vertices. As it goes up, the error goes down super fast. And in fact, with K equals 40 there, we're almost as good as neighbor joining, super high quality, even though we're really beating this system with high errors. So I went ahead and also looked at simulated alignments, much like semi, I believe. And again, you can see that the Robinson-Folds error here is pretty bad for the basic algorithm, starting with 3 sequences. So how does DNC3K go? Well, it does super well. Now we're seeing the K equals up to 200, right? So that is a little bit more aggressive or a larger number of sequences. But the number of leaves are up to 4,000. I mean, we can still manage to do this. And the quality difference is, of course, fantastic. And I was starting to think that, now it's so good, I want to compare with other tools. So I did that. And I picked RapidNJ, being so fast and nice. BioNJ, being a neighbor joining version, which has some very nice properties. And FastTree, which I think you have heard several people mention as a standard tool for fast phylogenetic inference during this conference. However, FastTree has speed because of an interesting way of using alignment profiles when computing distances in the first phase. And then it continues with a tree editing phase, improving on the neighbor joining method. And then it finalizes with a maximum likelihood-based cleaning of the tree. So the maximum likelihood I didn't want to bring in. That felt unfair to the other methods, so I turned that off. And the top graph here, as you see, that's when I'm also turning off the tree editing. And the result is so bad that it's hiding the result of the others. It's actually comparative to the basic algorithm I showed you first in quality. So if we remove that, you can see that it turns out that the DNC3K algorithm is performing super well. It's almost as good as FastTree with its tree editing step. And it's, to my actual surprise, much, much better than neighbor joining. And yeah, so what do we have then? Well, I have 2 scalable methods. One of them is super scalable, but also pretty lame. And then one method that is actually quite scalable, and useful and produces fantastic trees. I gave myself a standing ovation in my office when I saw that graph, actually. And I think it's very nice that you don't need a distance matrix for this. So we can start talking about MSA-free inference. And one can also start thinking about other distances. You might want to do distances based on structures, for example. And then suddenly this becomes a very cheap method to work with. So I've implemented this in simple Python, and it was so easy to write that I kind of over-engineered it. So I think you would find that it's actually easy to use as well. This is better than the average research software, I claim. And it's easily available both at GitHub and the Python repository. Thank you.
So I can't resist the opportunity to complain about the Robertson-Folds distance.
Oh, no, what?
Well, so if you have a tree with one branch in the sort of worst possible position, but the rest of the tree is right, you'll have a very bad Robertson-Folds distance. Yeah. And so, you found some of your methods were fast, but of the 4 that you looked at, some were fast, but had actually very bad RF distance. But do you have any insight into whether they were bad in ways that you care about for one application versus another?
No, I haven't studied the errors very badly. I want to say, though, that I am also suspicious about Robinson-Folds, but I picked it basically because most people know about it. I've also looked at Morea's tree matching distance. And yeah, you got lower errors, but the behavior was the same, and it took much more time to compute it. So I stayed with Robinson-Folds because of that. Regarding where the errors are actually turning up, it's probably different from Semi's experience there, because due to the base cases here, I'm expecting that there are few errors down at the tips, because the recursion will force the solid inference down to the leaves, basically. But I don't really know where the errors turn up.
Do I get to ask another question? Do you have a question? Well, so Semi looked to see if you use a particular tree, you looked at how your trees affect the outcome of, say, IQ tree, if you use it as your starter tree. Did you do anything like that?
I'm sorry.
Well, so one big application of today of neighbor joining would be a starter tree for a maximum likelihood method.
Okay,
and so then a measure of quality would be what's the final outcome from maximum likelihood.
I haven't done that, but that would be fun to do. But I was encouraged by this last graph.
I think you should be.
Yeah.
I'm up, we'll give you standard.
That we're so close to tree, what fast tree is doing with additional tree editing. If they can bring it down so nicely from a very bad starting point, then this is probably providing a good starting point as well.
So very nice to see the renaissance of the distance trees in these last
Isn't
talks.
it? Yeah.
But I don't know if you know, there's a paper that came out at MB very recently, I think called phylogeny or something like this, and they compare distance trees with maximum likelihood trees. Actually, the result that they're getting is that the distance tree are doing better on empirical data, which I think is going to make the phylogeny community lose their mind. But in any case, maybe you should compare, and then you might also get some surprising results.
I was not aware of this, but that's something I should definitely do. Thanks. Can I show you one more graph, though? Since I have them.
We'll give you a standing ovation.
Thank you. I'm so proud. This is a Python program, and you can actually in an hour, based on a very simple algorithm, compute the tree with up to 128,000 sequences in an hour with Python. And then you have to it's a little bit more painful when you're starting using the DNC3K algorithm. So, but still, isn't it fun?